Are you guys having a fantastic time? Isn't it good to see people again? 3 dimensions. Our next speaker is Joe Spisak. He is the director of AI product management at a company known as Meta, which I'm sure you've heard of. He's also the co-founder for AI Learning Alliance for Diversity in AI, and he leads the PyTorch library. How about that? So please help me. Oh, let me see. I've got a word for him. My word for Joe is AI community builder, because he's so big on helping people learn AI, making it understandable. So please help me welcome Joe.
Thank you, Beverly. Thank you all. Can you hear me? Awesome. Welcome. Yeah, it is good to see people in 3 dimensions. This is my first talk, I think, since before the pandemic. I got so sick of online talks. It was ridiculous. So it's really nice to be here. Yep, I'm Joe. I'm from Meta. And I need a clicker, actually. Well, I'm going to talk about grand challenges in math and science, and through AI and open science. And I was chatting with my friends over here, somewhere over here, and with the Home Depot crew. And I started talking about math and science, and everyone was like, okay, they eyes glossed over. And then I told them actually a little more, and they're like, oh, that's actually really cool. So hopefully everyone enjoys this talk. So just very briefly on me, thank you again, Beverly, for the great intro. I direct a product management effort in Meta AI. It's actually focused on AI research, so I'm less of a production guy these days. I spend a lot of time in prod, though. And I started this about a year ago in FAIR, focused on math and science. We have about 7 projects in synthetic biology, chemistry, multiple projects in chemistry, pure mathematics, human-machine interfaces in neuroscience, so how you interact with things in the future. These are all things we're looking at. I also spend part-time at a VC in Portola Valley, California, near where I live. So I'm an executive in residence there. I also advise informally and formally lots of startups, which is kind of fun to hang out with founders. Previously, as Beverly mentioned, I spent about 4 years leading PyTorch, a product team focused on building a library for ML authoring. So if anybody's used PyTorch, like, shout out. Awesome, great library, great community. Great things are still to come there. And I was at Amazon and Intel prior, and then I spent an entire decade of my life in the chip space, building SoCs and doing everything you can kind of do in the semiconductor world. So today I'm here to talk about math and science and grand challenges, though. It's a space that's truly being disrupted through AI. And I'll talk through some of the reasons that I believe this is happening. And I will actually walk through a little bit of chemistry. So if anybody's taking chemistry, I actually never took it, or I took it in maybe it was high school, and I took some in undergrad when I was getting my double E. So it's been a while. So I had to relearn a lot of chemistry when I took this role and started building this team. And then I'll just give you guys some closing thoughts I have on where this space is going. So starting with the grand challenges, this is, when you think about math and science, it's super broad. And one of the things that when we set up this team about a year ago, it's great to have a challenge, something that's basically close to impossible that you're trying to achieve. Things like building AI that can help create green energy or help fight climate change. Like, I actually have a whole team that works on this. Therapeutics and vaccines for the next pandemic. I mean, we're still living in the current pandemic, I guess. I mean, I have 3 shots in my arm from Moderna. Their AI-driven, mRNA drug or vaccine. So I'm super proud of what AI has done there. Things like new materials. Like, how do we basically find new materials for new form factors of devices, new applications, and then lastly, things like co-learning with AI. How do I learn faster? How do I build AI that allows me to interact with machines, make me better, allow me to communicate in different ways, move beyond that QWERTY keyboard possibly that's been around for so long. And so what's fundamentally happening here is that AI is disrupting the scientific discovery process. And I'll talk more about kind of AI and computational and experimental, but these worlds are kind of colliding at this point. So as Joel mentioned, there's cutting edge models. We talked about BERT. I mean, BERT is kind of like 4 years ago, but it was the start of the transformer revolution that's been happening. But these models are disruptive. The models are powerful. They can do great things, and actually in these domains, they can actually have transformational impact. Things like high throughput experimentation. If anyone's heard the term self-driving lab, probably not. It's a pretty niche part of research right now. But how do you fully automate, like with robots, basically such that you can experiment and you actually can operate in the real world and actually match these computational and AI techniques with something that actually is real? Things like cloud labs. If you're a biologist, this is a boon, right? There's this concept of a wet lab, right? I have a result, I have to synthesize something, put it in a real lab with test tubes and containers, and now this is actually turning into AWS, right? You can actually do this as a service. And then things like digital twins. How do I optimize in kind of this industrial kind of metaverse area? Maybe simulate, look at different scenarios, and then match that with the real world and actually optimize what's happening in real life. And then, of course, areas like computational design. How do you flip that on its head and think about this kind of an AI-driven approach? So all this is actually leading towards this discovery process being disrupted, which is super exciting. And so when you take a concrete example, so has anybody heard of this kind of concept of the unpredictable arts? So maybe a few folks I see. Okay, so you think about like the old school companies. I won't name them because I want to protect the innocent. But they have these massive databases of proprietary compounds, molecules. They're large. They're probably incomplete, but they've been building these for decades. And then what they do is they experiment, right? They take them into the lab. They synthesize something, or they crystallize, say, protein, whatever they're trying to do. And then they validate them either experimentally or computationally. This is kind of order days or weeks. So you can imagine I have millions of molecules, potential compounds, and then I'm trying to validate these things, and you can obviously do the math, right? Millions times weeks seems like kind of an intractable problem. And so when you look at these areas like material science, chemistry, and pharma in this kind of unpredictable arts regime, you could be looking at something like 10 to the 11th, even up to 10 to the 60, type of molecules, depending on the field, which is an insane number. It's an insane search space to kind of to go through. And so the question is, I guess, can AI help? And so as an AI guy, yes, I absolutely think we can. I think it can do something here, which is why I want to tell you more about this. But I guess taking a step back, and I want to talk a little bit more about what's driving all of this. Like, what are those major drivers? One is scale. As Joel mentioned, I stole this from my friend Julian Simone, wherever he is, Hugging Face. We used to be colleagues at Amazon, and this is the golden age of AI. This chart kind of shows the last few years. Obviously, not all the models are on here. Palm isn't even on there. That's 540 billion parameters. I don't even list the diffusion models, which are all the rage right now with, of course, generative imagery. But scale is disruptive. And it's really cool that you can create an autoregressive language model that generates some text. What's really cool is actually when you can actually use it in things like protein sequences and actually fold proteins more accurately than ever before, which is kind of what's happening right now. Also, data is disruptive. So this is just kind of the perspective through Meta, but we have a lot of data. We generate a lot of data through our pipelines, our production pipelines. So you can I won't walk through all these numbers, but you can kind of see we have on the order of 1,000 pipeline authors who generating kind of an order of magnitude more pipelines at exabyte scale data warehouses, on the order of millions of machines in our data centers. And you can see in production traffic on the order of 100 petabytes of data, so massive scale data. The challenge, of course, with math and science in some of these more esoteric areas is, that data doesn't exist, or that data tends to be in places that are hard to get to, or needs to be mined, or needs to be developed in some way. And then the third leg of the traditional stool is compute. And for example, like in our side, in FAIR, where I sit, we just built a research supercluster that's on the order of 5 exaflops of compute. It's about 14,000 or 15,000 A100 GPUs with super fast interconnect, tons of storage. So it's basically, we have our own top 5 or whatever supercomputer for our research, which is pretty nice to have. So that's kind of like the major drivers of scale. But to actually scale this up, you need access to that compute. Anyone have trouble getting 1,000 GPUs on AWS these days? You're not the only one. I can't even. I have a lot, I have research budget and I can spend it. It's nearly impossible. So access to it, but also access, for on the order of months, because some of these models take, 2-3 months, and that's after you've done a ton of experimentation and you've been able to kind of lock your hyperparameters and so on, and learning rate. So it's difficult to get compute. Researchers with scale expertise. So anyone who's tried to hire any of these researchers that kind of sit at that intersection of AI modeling and SysML and like systems, they're incredibly expensive. They're all going to high-funded startups, big companies like Meta and Google. So they're also difficult to acquire. Big curated data. This is actually probably the most understated bullet here. The scalers I know, the ML scalers that are training the largest models in the world, they actually spend most of their time curating data. It's the right data, right? It's they prep and clean data. They do a lot of the things, the dirty work that frankly doesn't get all the press, but it's actually needed to get those models that perform at the levels they do. Framework engineering. So I'm lucky enough to have the PyTorch, or most of the PyTorch engineering team within very close proximity to me. So when it comes to looking at ways to shard these models over lots of distributed computing elements, I pretty much have to walk over or hit up somebody on chat. That's pretty powerful. So when we develop, for example, the fully sharded data parallel algorithm, which is used for a lot of these larger models, I had that team sitting right next to me, and we were basically doing co-design for some of the models we did. Research problems. I think we all talk about large language models. They're super cool. They generate interesting text. The diffusion models are a lot of fun to play with. I think, though, personally, where we're going in the future is actually interesting applications and research problems. I think that it's really fun to do these generative models, and there's ways certainly to monetize them. But really, the parameter counts are not that exciting anymore. It's more, I would say, actually the impact and the applications. And then lastly, if anybody's had to ship one of these models in production, holy cow, the privacy, the policy, the legal, the comms, the ethics, the marketing, everything that goes along with releasing these things is complex, right? These are models that are incredibly powerful. They can do great harm. They can also do great good, of course, and they do. But the complexity is incredible. Just even shipping these things. And the really cool thing about my team is we actually do a lot of this in the open, right? My team actually at Meta has actually released, the OPT model, which is 175 billion parameter model, is publicly available. You can download it, you can play with it, you can fine tune it, you can do whatever you want with it. And so we're incredibly open. So reason number 2, this is actually kind of in the next couple of years, is the experimental capabilities are democratizing. So you remember kind of this flow. We had this this AI-guided discovery. This is the large-scale models, data, domain experts, say computational chemists or biologists. It's great. You can develop a model and you can push a benchmark, and certainly you could write a paper, and that's fun, but really not that impactful, maybe. In the chemistry world, in the materials world, you'd verify something computationally, because there's this, you can either go back all the way to Schrödinger's equation, or you can do an approximation, which is called density functional theory, and I'll talk more. But you need to be able to verify that your results are correct. And then you can actually validate this in the real world. But how do you do that, I guess, is the real question. And one of the coolest things that's happening is, I mentioned this in kind of the intro, is the world of Python and AI is actually starting to collide with the space. So the self-driving labs, if anybody's seen companies like Stratios or Emerald Cloud Lab, you can essentially program and control lab equipment and automated robotic equipment that does all this for you with Python. So if you can write Python, basically you can operate a wet lab, which is incredible. And the same thing is kind of disrupting in the chemistry space as well, in materials. And so what we're starting to see is there's startups and there's academics that are kind of leaning into this innovation. And it's no longer like, I got to go to UCSD to like crystallize my proteins and like spend, all this money, and it's a few like, academic labs that hold all the cards. Like, this is truly democratizing these capabilities. This is actually going to innovate. There's a lot of people innovate much, much faster, because the power on the AI side is community. It's models are moving faster. They're more performant, more powerful. We have computation. We can do DFT, and then we can take those kind of in silico computational results and actually then turn that into something real and do it in a way that actually is at the speed of ML. And then the third reason, which is of course near and dear to my heart, is the open science piece. So when you look at open science, what that concretely means is making scientific research and the dissemination accessible to basically everyone. This is, of course, your Wikipedia definition here. By the way, can you move the cursor off the slide? It's sitting kind of right in the middle of the text. And so what does this mean to Meta? So one of the things that we're super proud of is our open research. And so when we think about open and open science, we think about AI software, so PyTorch, right? We open source the model code that we use to develop models. We'll open source data sets, which I'll talk about. A couple big ones we've actually open sourced fairly recently. The models themselves, the model weights. Again, we've probably spent 8 figures in some of these cases training these models. We're going to put those out and basically allow the community to use them and fine-tune them and build applications around them, and that's pretty cool. And then obviously we publish transparently, so we put papers on archive. We write articles, we blog, we do all those good things. And then lastly, one of the coolest things that we do is actually have leaderboards and challenges. And the project I'll talk about today actually has a great leaderboard. And this actually allows the community to kind of have a direction to go, right? They have a benchmark, they have something aspirational. They can kind of see what the rest of the community is doing. So it kind of gives a center of mass for what's happening. And so when you kind of take a step back and you look at the reasons why open science is important, besides, it's good, right, to be more open, one, there's these hidden dangers, right? These models have hidden dangers. There could be bias in them. They could be used, obviously, for great harm, the more powerful they are. And I think, if I had to choose between being kind of closed and paternalistic or being open and having more people, playing with these things, doing research on top of them, I'd absolutely choose the open route. And so I think that openness helps us, I think, counteract those hidden dangers. Second is reproducibility. So in any scientific field, like to build on someone's research, you kind of need to be able to reproduce what they've done, and you say, okay, how do I then go from here to build something better? And I would say in AI, we're not quite there. We've been trying for a long time. There's reproducibility challenges. There's Jupyter notebooks, if anybody has used Jupyter. But there's still like a lot that goes into research. We still have interns that spend their entire summers trying to reproduce an important paper, and that's crazy. But still, we open source our code and models, and we try and make our work as reproducible as possible so that others can build on top of it. And then lastly, I would say with some of these problems, no company or no team can do it themselves. Like in climate change, for example, we plan to work on a number of different major issues, and we have teams in flight that are developing technology, and we plan to open source that and collaborate openly with others wherever we can. These problems are just too hard. They scale in a direction that just no one entity can solve. So this is where openness comes. And actually, when it comes to IP, like if you look at other industries, like AI has been very open about IP. Like if you look at the code that gets developed, not only by Meta but many others, it's licensed in a way that's commercially usable. The models get generated and they're Creative Commons licensed, so somebody could take them and use them. So this allows others to come together and actually work together. So I'm going to shift gears and talk chemistry. So I won't go too deep in a few things, but I will hit a few kind of terms and And feel free to ask me questions. I can't guarantee all the answers. I'm not a chemist myself, but I'll do my best. I have a team of computational chemists and AI people that are way smarter than I am. But I will walk you through kind of what we're thinking and what we're doing. So if you haven't checked out this project, it's one of my absolute favorite projects. And yes, I'm biased because they're part of my team. But the Open Catalyst project, it was started a few years ago. Definitely check it out. OpenCatalystProject.com, I think it is. You Google search it, you'll find it. But the goal here is basically to find a new catalyst material, so using AI. And what we found actually is this project has become kind of a blueprint, or actually developed infrastructure that allows us to scale to many other problems. And the reason this is important is, catalysts today are expensive, right? You have palladium, platinum. When you think about like fuel cells and these types of green energy sources or storage areas, a catalyst is needed, and that's actually one of the limiting factors. And so what is a catalyst? I think everyone's probably taken chemistry, maybe, I don't know. So I threw this slide up. It's a material used to increase the rate of chemical reaction without being consumed in the process. So this is your middle school or whatever chemistry definition. And so why is this important? Well, believe it or not, a couple of different, actually there's not very many like storage options for energy these days. So there's like the Tesla battery farm. So if you've seen that, it's like $50 million. It's 129 megawatt hours to build that, and it's kind of a drop in the bucket when it comes to how much the energy that gets produced by the U.S. population base, or the U.S. generation. And then second, has anybody heard the fact that we pump water uphill to store energy? 2% of our energy that's stored is from pumping water uphill. That seems, when I heard that was crazy. I thought, this is the stupidest thing I've ever heard. So why are we doing this? Well, because it's actually, believe it or not, it's 70 to 80% efficient, which is actually good in some ways here. So, but there's got to be a better way, right? And this is why there's technologies like green hydrogen that are being developed. But of course, they have cost issues. Things like catalysts are not available. Everyone's trying to solve this problem, so we can actually make these next generation energy storage technologies more viable. So abrupt topic change. I mentioned DFT earlier, density functional theory. What this does is it's a computation, it's an approximation of Schrodinger's equation. So you can go and you can look up Schrodinger's equation. You probably won't recognize all the terms, but you can find a video on YouTube, I'm sure, that'll tell you about it. And what this does is actually computes the system energy on per atom forces. And what this does, you can see these kind of cool little animations here. So these are molecules basically sitting on a catalyst, and what we want to do is actually find the positions that allow for the lowest energy. We call that a relaxation. And what that relaxed energy actually tells us is what the reaction rate is. So that lower energy, that relaxation, actually will tell us if we have a good catalyst or a better catalyst, and then we can actually apply that to kind of these large databases. Challenge is those databases are massive. So you have lots of materials, you have lots of surfaces of those materials, you have lots of binding sites. So this is kind of this, this problem where you have lots of combinations. And so this is a snapshot from some of from the data that we actually generate, which I'll talk about in a few slides. So we literally have billions of possibilities, and you can't possibly run a DFT because it takes 8 hours on, say, traditional compute to actually run a DFT. So if you can imagine like billions times 8 hours, that doesn't quite add up. That's a lot of time. I'll probably be retired by that time, hopefully, by the time we actually did it. So the good news is, we're talking about AI, right? If we could approximate DFT with ML, we can turn that 8 hours into 1 second, which is pretty cool. And so the great thing about the ML community is everyone is always optimizing things. So this is, if there's something good that can come out of, like, say, a new model, say when the Transformers models came out, somebody built, the Hugging Face folks, I think it was Victor, they built the Stillbert, and that took basically like BERT into a regime that was actually possible to deploy into applications. Like, people are optimizing things. That's the cool thing about the AI world. And so this second actually might even be lower at this point. And what that allows us to do is actually turn this into a brute force computational problem that we actually can throw our infrastructure at. And it allows us to basically scale to these super large databases and actually find that needle in a haystack that might allow us to actually unlock some of this technology. And so what's great is we can actually use some of these models like graph neural networks. So graph neural networks are a great way to basically articulate like really complex or rich information. So if you haven't played with GNNs, they're really cool. In this case, the node is an atom and the edge is actually the neighbor. And the input to this model is actually the 3D atomic positions and the atomic number, and the output actually is the forces from the atom. So we're taking basically kind of a traditional GNN, which might be used in, I don't know, social graphs or whatever, like by Twitter, by Facebook, and we're actually taking this into the scientific regime and actually using it in chemistry. And so we built a bunch of these kind of models, and what we found is, first of all, they take forever to train. This is on, albeit this is not a ton of GPUs, it's on 64 GPUs, and we use mixed precision training. We use AMP from NVIDIA. We train a bunch of these. Some of them take like 1,000 days to train because they're just really complex and expensive and lots of data. More importantly, though, the inference time actually is what's important. So by the way, lower is better here in these graphs. And the further you can reduce that inference time down, the faster you can actually predict on these materials databases. So I can actually, again, turn this into a brute force problem and actually find materials much quicker, and then I can then go back to my validation in an experimental lab, create those materials, try them out, experiment, and ultimately, hopefully, ship something in production. The problem is we need lots of training data, and this isn't ImageNet, this isn't Coco, this isn't something that you can just download off the shelf. We actually need to generate it. And so one of the really cool things here is we actually generate these data sets and we actually open source them ourselves, and then the whole community kind of rallies around them. And so as an example, we have a couple data sets we've open sourced. They're quite large. This is the OC20 data set from 2020, and then we just released the OC22 data set, which is actually even larger. And to kind of give you an idea, we actually generated this over 200 million plus CPU hours on renewable energy, which is really cool. And this is actually compute. So when you're not on, for example, Facebook, our infrastructure is relatively, it's loaded. It's not loaded, with usage. Like we can actually use kind of compute that's available, and it's again renewable energy based. And then we generate these data sets. It takes us, on the order of a few months to generate these data sets on this kind of large scale compute. And then we basically open source it and permissively license it, which is super cool. And we've seen, Berkeley, we've seen Georgia Tech, we've seen Stanford, we've seen all these top labs in chemistry start to use our data and start to build on it. And yeah, it's incredible. And so, you can go to the Open Catalyst site. We have the paper, we have the data, we have the code, leaderboard, there's discussion. We have really great submissions on the leaderboard from academics. Our friends at DeepMind submitted a bunch of models, which is cool. So, hey, we can all be friends. We can all work together on hard problems and address climate change. So a few parting thoughts. I just have 30 seconds, so this is perfect. One is, AI definitely has the potential of being incredibly disruptive in the scientific area. I think this is really cool. This is what gets me out of bed in the morning, and we can actually have some transformative impact from this work. Second, scaling an AI, Cloud Lab, or these experimental capabilities as a service, as well as things being open. If you look at the chemistry space or material space, these kind of old school companies are traditionally not very open. But the good news is, AI kind of started from, an open perspective, right? It was open science. 10 years ago when I got into machine learning, I got into it because it was open, because I met people from Google, NVIDIA, Facebook, academia. They were all working together on open source projects. And it wasn't like, okay, we got to hoard our IP over here. It's, hey, how can I help, fix that or build that, or oh shit, CMake's broken, I'll go fix that. So like that really drew me in. And it's very different than the video space that I spent the last 10 years in, where there was patent pools and everyone's trying to hoard essential patents and all that stuff. So it's super exciting. There are challenges, I would say, though. These bridges aren't fully built. There's definitely an ethos that's different in, in say like the experimental space versus say the AI in computational worlds. But we're getting there, right? People see the value in this. We had that AlphaFold moment in synthetic biology. There's one coming for materials and chemistry as well. And just lastly, get involved. I think get involved with one of these projects. Again, we're going to be open sourcing our work, so we love collaborators. We love people to contribute and help us address some of the biggest challenges. So I will pause there and take any questions you have.
We're out of time for questions. I'm so sorry.
Okay. Well,
Thank you.
Catch because you have.